Hello, here's a few magnetic field questions. We're starting here with a horizontal current carrying wire in a uniform magnetic field. The magnetic field of flux density 0.07 Tesla, right angles to the wire in the plane of the paper. Right, the weight of a 1 centimeter length of the wire is that. Okay, current I is such that the vertical upward force on the wire due to the magnetic field is equal to the weight of the wire. So calculate the current I in the wire. Right, so we know that our force on a current carrying wire in a magnetic field from our F equals BIL, we don't have to worry about any angles because they've told us that magnetic field is at right angles to the wire. So we've got that, and that is equal to the weight because they've told us that as well in the question. And we need to calculate I. So I is going to be equal to the weight. What did they tell us the weight? So that's 6.8 times 10 to the minus 5 divided by B times L. B is 0.07 and L is a centimetre, so 0.01. So that's going to be, well, all of these minuses are going to be cancelling. We're going to get 6.8 over, oh, not almost cancelling, 6.8 over 70, which is 0.09714, is what my calculator tells me on that, which is then 0.097 amps. So two significant figures. Suggest why it would be impossible for overhead cables carrying an alternating current to float in the Earth's magnetic field. Right, well, this is because the force will keep changing direction. Force will change direction as direction of current changes. The current changes. So, I mean, well, that's it really, isn't it? So, well, we could say, I suppose, to be really clear, the force due to of the magnetic field on the wire, magnetic field on the cables. So yes, the force of the magnetic field on the cables will change direction as the direction of current changes. Right, so there's got to be more to that. That's too short. Yeah, here we go. Charged particle enters a region of uniform magnetic field. Figure 2.2 shows the path of this particle. Okay, so it's going in a circle. We've got the direction of the field is perpendicular to the plane of the paper. Magnetic field has flux density B. Particle's got mass m, charge q, speed v, travels in a circular arc of radius r. Derive an equation for radius r in terms of b, m, q, and v. So we got our force on a charged particle due to the magnetic field is b, q, v, and that is going to be equal to our centripetal force because we're moving in a circular arc, so it's going to be equal to mv squared over r, and we just need to rearrange this to make r the subject. We can cancel a v on either side and say that r is equal to mv divided by bq. Right, a thin aluminium plate is now placed in the magnetic field. Right, figure 2.3 shows the path of an unknown charged particle. Okie dokie. The particle loses some of its kinetic energy as it travels through the plate. The initial radius of the path of the particle before the plate is 4.8 centimeters, and afterwards the radius is 1.2. Right, so the radius has dropped down by a quarter. Right, so what do they want? Calculate the ratio of the initial kinetic energy to the final kinetic energy. So we can say, so the radius of path is 1/4 initial radius. So this is one of our usual logical chain things that we're doing. Therefore, we can see here that the radius is proportional to the velocity, because the mass hasn't changed, neither has the magnetic field strength, the flux density, or the charge on the particle. So they haven't changed. Therefore, V is 1/4 of initial velocity. Initial velocity. Yeah, maybe we should say speed, but initial speed, because it is going in a circle. So yeah, let's go with speed. Right, so V is 1/4 of the initial speed. Therefore, kinetic energy is going to be 1/16 of initial kinetic energy. Now we can get on to doing our ratio here. So the initial kinetic energy divided by the final kinetic energy is going to be 1 over 1/16. Therefore, ratio is equal to 16. Yeah, so the usual sort of thing that we do in these logical chains. Right, that should be the end of that question, and it is. Figure 2.1 shows the circular path described by a helium nucleus in a region of uniform magnetic field in a vacuum. Right, so it's going round and round in a circle. Direction of the magnetic field is perpendicular to the plane of the paper. They've given us the magnetic flux density, the radius of the path, charge and mass of the particle. Right, they've given us everything really. Explain why the helium nucleus travels in a circular path. Right, so there's a few things we need. We need to say there is we want a constant force, because if it wasn't a constant force, it wouldn't be a circle. It would be spiraling inwards or outwards. So we want a constant force, and then we want to say that that is acting perpendicularly. It's always hard for me to say, to the motion of the, what is it? It was a helium nucleus. Motion of the helium nucleus. So that's why it's going round in a circle. And then we have to explain why it has the same kinetic energy at A and B. So we're saying, well, there's no work done, obviously write out work done, just saving some space, by the force on the helium nucleus, because it is perpendicular to direction of motion. Right, so that's fine. Now they want us to calculate the magnitude of the momentum of the helium nucleus. Right, so we're doing our usual, so like we had on the last question actually, BQV is equal to mv squared over r. So, and we want to work out the momentum, so we'll just leave mv as the, let's cancel the v's, and then we can say, well, bq times r is equal to the momentum, which is what we're after. So what is all of this? We've got b, where's b? 0.2 times 10 to the minus 3. Q is 3.2 times 10 to the minus 19. And then we've got R, which is 15 centimeters, so 0.15. So that's going to give us our momentum as being, actually these are quite nice numbers, because we've got a 3, so we're going to have a 9.6. That's taken care of those. And then how many minuses have we got? We're going to have 22, 23, 24 times 10 to the minus 24 kilograms meters per second. Calculate the kinetic energy of the, right, okay, so kinetic energy is a half p squared over m. They've given us m, so we need to do a half times 9.6 squared times 10 to the minus 48 divided by this mass, which is 6.6 times 10 to the minus 27. Right, so we're going to get a slightly annoying number out of all of this, aren't we? But what are we going to end up getting? Well, 9.6 over 6.6 is 16 over 11. So, and then we can halve the 16 and say 8 over 11. So, and then 8 times 9.6 is 76.8. So 76.8 over 11 times 10 to the, what have we got left on this? 21 minus 21. So, yeah, I mean, that's just short of 7. Let's go to the calculator just to see. 6.98 times 10 to the minus 21. So 7.0 times 10 to the minus 21 joules. I've run out of space to actually write that out in 2 significant figures, but you know, whatever. The part B, a uniform electric field is now also applied in the region shaded in figure 2.1. The direction of this electric field is from left to right. So I put an electric field in going left to right. And that's the direction it pushes positive charge. And this is a positive charge. We've got a helium nucleus. Describe the path now followed by the helium nucleus in the electric and magnetic fields. Now, well, the magnetic field is still going to be making this go round in circles, but we've now got this additional force, which is going to make it sort of spiral off to the right, because we've got 2 effects going on now. So we're going to get, rather than a circle, we're going to have something that's looking sort of like this, going off to the right. So, I mean, that is describing the path. I think just drawing out a picture will suffice on that one. So that's fine. Right, I'll do one more, I think. What we got next? State Faraday's law of electromagnetic induction. So this is the induced EMF is proportional to the rate of change of flux linkage. Remember, the equality comes in with a -1 when we add in, was it Lenz's law? Rate of change of flux linkage. So for, I think they let you get away with putting an equals there, but yeah, at least from a historical point of view, it's the proportionality there that we're interested in. Part B, figure 5.1 shows a magnet being moved towards the center of a flat coil. The current is induced in the coil. Use ideas about energy conservation to state and explain the polarity of the face of the coil nearer the magnet. Right, okay, so remember with Lenz's law, we're setting it up so it's opposing, will induce an EMF that opposes the thing that's creating it. So you must have a north pole that we're pushing against. So that's the first thing that we need to say. We will say polarity is a north pole because, well, let's say so that the a repulsive force is established and the work done against this force is transferred to electrical energy. Against this force is transferred to electrical energy. So again, I'm doing the usual shorthand that you'd want to actually avoid, but it's just to save a bit of time. Right, so that's part B. Good. Figure 5.2 shows the magnetic field from the North Pole of a vertically held bar magnet. Right. The small flat coil is placed at A. It's moved downwards from position A to position B. Right, okay, I just slid it straight down from top to bottom. The plane of the coil remains horizontal between these 2 positions. Explain why there is no induced EMF across the ends of the coil. Well, you can see it from the picture here. We've got these 3 lines linked to the coil when it's in position A. We've still got the same 3 field lines, haven't really changed when we're at position B. And as we said in part A, we need a change in flux linkage in order to induce an EMF. So we can just say here there is no change in flux linkage. Flux linkage in the coil. Yeah, let's say in the coil. In the coil. Oops, coil. Right, there must be more again. And there is, right, so we've got graphs. Right, figure 5.3 is a graph showing how the magnetic flux density, B, varies along the line X and Y in that previous picture. All right, okay, so moving it from here on the left over to Y on the right. Okay, right, so yeah, that's how that's changing. The same flat coil is moved at a constant speed from X to Y. Plane of the coil remains horizontal between X and Y. On the axis provided at the bottom here, sketch a graph to show the variation of the induced EMF across the ends of the coil with distance X. Right, okay, there is a little bit of ambiguity on this because we don't know how wide the actual coil is, and that is going to matter because, okay, we know that if there's no change in the magnetic flux density, then we can't be inducing an EMF. You know, we need a change in magnetic flux linkage, and in this case, because it's perpendicular to everything that's going on, we're going to have B. You know, the coil is perpendicular to the magnetic field, so our magnetic flux is BA because they're perpendicular. Then we need to multiply the number of turns in the coil. So something's got to change in this. We know that A and N, they're not changing. We're not adding coils or changing the area of the cross section of the coil. So it's only when we've got B changing that we're going to induce this EMF. Now we can see that B is changing only in these two parts here. But of course, the width of the coil does matter because as soon as you start pushing a bit of the coil into the magnetic field, you've got a change of flux linkage, even though the center of the coil might not have reached the magnetic field at that point. But we don't want to get too bogged down on this. Really, we want to be saying that we've got nothing going on at all up to, let's say, up to here. Up to 3. Let's say that the width of the coil is really negligible. So we'll go, that's flat. We'll have it flat between 5 and 8 for the same reason, because B isn't changing. Okay, we might have a magnetic field, but it's constant, and we need it to be changing. So we'll have it flat there, and then we'll also have it flat after 10. So we've only got 2 bits where it's changing. We can also see that the rate of change is in a different direction. So we've got we've got an increase here, positive increase in gradient there, and then we've got a negative gradient here. So we're going to have to use both sides of the axis, and we're going to get a pulse. It doesn't matter which way we go because we can, you know, decide our EMF. You know, you can draw it in either direction really, change the polarity around. So yeah, so what we're going to do then, we can also see that we got a much the gradient is increasing here. So we're getting a larger change in B here than we do there. So it's going to be increasing. So we're going to have maybe something like, well, yeah, something like this. Let's do something like that. You'd have equal and opposite. So down to sort of there and that sort of look, those sort of pulses. So it's lopsided. I don't think in mark schemes, from what I recall in the past, that they get too fussed about the shape of the pulse. The things that they're going to be looking for is you've got these 3 flat sections where you've got 0 induced EMF. So you need to have 3 of those. You need to have 2 pulses which are opposite to each other. They're going to have equal and opposite shapes and magnitudes. So that's what they're going to be looking for in these. It won't matter too much how you've drawn the pulse. Right. Yes, I'll leave it there for those 3 and then come back for another couple in the next video.